Hello everybody. Today I'm going to create a tutorial video on knapsack problem, a video which has been suggested by the people from Discord server. Their suggestion was mainly about the more advanced parts of the knapsack, which are not covered by any video or tutorial on the internet. But in order to also make it easier to watch for the beginners, I decided that I'm going to explain everything you need to know about the knapsack problem from the beginner up to the higher levels of competitive programming. In order to actually make this easier to watch for everyone, I will let some timers in the description, such that if you, let's say, are looking for a certain organization, you can check out the description and start watching the video from that moment. So you don't waste your time watching things you already know quite well. Now let's begin the video by explaining what the knapsack problem is. So the knapsack problem is a problem in combinatorial optimization, and we are given a set of items. Each item has a weight and a value, and we need to choose a subset of items such that we get the highest possible value, while also not exceeding the capacity of a knapsack already given in the input. In this image, in this right part, we have a knapsack with 15 kilograms, and we have these 5 items. And if we can only take one item, like we can, let's say, take 2 greens or 2 yellows, then the solution would be to take every item except the green one. And that would lead us to a $15 profit while filling only 8 kilograms of the knapsack. So you don't actually have to fill the entire knapsack in order to get the optimal answer. Things can differ from input to input and also from variant to variant. Now, I'm going to continue this video by explaining the types of knapsack problems and also giving examples of problems where you apply them. The first and the most common type of knapsack problem is the 0-1 knapsack. The 0-1 knapsack is quite simple as in terms of knapsack problems. So we have n items and the maximum weight W. And we obviously know for each item its value and its weight. And we can only take one item of each type. Like we can't take, let's say if we have an item with value 3 and weight 1, we can't take it 3 times unless it appears 3 times in the input. But if it appears only once, you can't take it 3 times. And the goal is for all these knapsack problems to fill a knapsack with a given weight such that we get the highest value. Now, for this problem, there are actually multiple solutions we can use. If we have few items, we can just create all the subsets with a brute force algorithm. So if n is, let's say, up to 20, you can create all the sets of items you can obtain in of 2 raised at n, and you can actually take just the biggest value we can get as long as we fulfill the weight constraints. Now, in real life, you may not have only 20 items, you may have more, so you need to think at more advanced concepts in order to solve this problem. Actually, there are 2 solutions widely used for this knapsack problem, but sadly one of them is not correct. So I'm going to mostly focus on the correct one while also explaining why the wrong one is not correct. So the correct solution for solving the 0-1 knapsack is the dynamic programming approach. And how can we actually create the dynamic programming in order to solve this problem? So let's say we have these n items and each of them has a value and a weight. And the maximum weight is small enough in order to actually allow us to store the memory required for it. So we can actually create a recurrence which is dp of I and j, which is the highest value we can get if we chose among the first I items a subset of them such that we have weight j. And from a state ij, we have two options to go. Let's say if we have the next item, the I plus 1 item, we can either take it or not take it. If we take it, then we are going to check the state I plus 1 j plus the weight of the next item and updating it with the value of the I plus 1 item. And the other option, if we don't take it, then we will go to I plus 1 and j. Because we don't take it, we don't add any value either or any weight. So there is no point in adding anything. In order to implement this DP solution, you have a complexity of n times w, because you have n times w states. And the memory is n times w. But this solution can be optimized by observing the recurrence. And the easiest optimization to come with is the memory one, since from a state ij, we only go to states which have I plus 1. We can use a quite well-known optimization in dynamic programming, which is the two-line optimization. So instead of storing, let's say, dp of n plus 1 and w plus 1, you only have to store two lines, dp of 2 and n plus 1, w plus 1. And instead of going from I to I plus 1, we are going to go from 0 to 1. But the thing is that in order for this to work correctly, you need to actually do mem sets in order to shift the values. So the old 1 positions will move to 0, and the old 0 will be discarded. So like if you have 4 items, you are going to do this mem set 3 times. After the first item, after the second one, and after the third one, in order to still allow you to do the right thing. I said earlier in the video that I'm going to also discuss about a wrong solution, which is implemented quite often by the less experienced people. So let's say they have also n items and at most w weight, and they don't know the dynamic programming solution, or they might have forgotten it. There is also the greedy solution, which sorts the items by the ratio v divided by w, and they take greedily the items with the biggest ratio because they would think that it's the right thing to do. But sadly, in some inputs, this is not exactly what we want. Like, let's say we have 3 items. So we have 3 items and at most 5 weight. And the first item would be, let's say, an item with weight 3 and the value 10. But the other item would be something like, I don't know, 3, 1. And 10 divided by 3 is bigger than 3 divided by 1. But in this case, wait, for this case it works. Sorry about that. The grid actually works since you can take this one and this one twice. But it's not too hard to figure out a case where the greedy solution would fail, because you would basically need some close ratios, but taking the first item would forbid you from taking the second item, which is easy to observe. Now, we can't really say that the greedy algorithm is 100% wrong, because there is a variant of knapsack problem which shows up less frequently, but it still shows up, which is the fractional knapsack. And in fractional knapsack, you can actually break items. And let's say if you have 10 and 3, you can actually break it in something like 5 and 1.5, or any other break you want. And this actually allows you to sort the items and take the highest ratios. Now, I'm going to continue with showing an example of an implementation for the 0-1 knapsack, along with a problem which requires using the 0-1 knapsack. So here we have a problem from the educational DP contest on Uncoder, which is knapsack 1. And we are given n items, and each item has a weight and a value, and we can choose some of the items such that we get the maximum weight while not exceeding the W. And this is literally the example I explained earlier, and it is solvable using the DP recurrence I explained earlier. Now I'm going to show the implementation while also explaining what I'm doing there. So here is my implementation. I have a DP array. In this case, since the memory is big, I didn't have to use the two-line optimization, but in other problems it may be necessary. In Autocoder, they actually give some constraints which are fine for the contestants, as in they don't really force the contestants to optimize as much as they can. They are pretty relaxed about it, and that's why I actually didn't overcomplicate the approach as well. So, as I said in the earlier part of the video, dp of ij is the maximum value if we fill the knapsack with some of the first items, and the total weight is j. And when we do the knapsack, like when we solve it, I iterate over the items, and I always assume that I add the next item. And I either add it or not add it. And if I add it, then I have to be careful to not exceed the maximum weight, because that may give us nasty results. Like it can either be a runtime error or an undefined behavior. And both of them will lead us to wrong answers, or to actually a runtime error. And at the end, all we have to do is to find the maximum weight among the first W items, and that will give us the result. Now I will continue with explaining another problem which is similar to this one, but which involves an optimization, or more like a different thinking based on some different set of constraints. So there we go. We have the knapsack 2 problem. The problem has exactly the same requirements, but there are two things which are very important, which are different. The maximum weight is up to 10 to the 9th, but instead the value of each item is small, up to 10 to the 3rd, which is 1000. And in this case, we can't use the same recurrence anymore, because n times w is way too much in terms of time and memory. But we can observe that the sum of weights is quite small. Like if we multiply 100 by 10 to the 3rd, it would be 10 raised to the 5, which is good enough in order to actually allow us to use a solution which runs in O of n times the sum of the values. And the approach is actually quite similar, as I'm going to explain in the solution. So there we go. As I said earlier, it's slightly different. So dp of I is the minimum weight if we fill the knapsack with some of the first items, and the value of the items is j. And as you can see, the solution is quite similar, except we need to be careful about which items are we going to continue with. At the beginning, we have to initialize the dp values with a big weight, such that we don't consider values which are not correct. And the recurrence is pretty much identical, except you need to be careful at the dimensions, because instead of position and value you have position and weight. So you need to be careful about it. Now I'm going to continue with explaining the bounded and the unbounded knapsack before we go to the harder problems involving the knapsack tree, the knapsack problem. So we have the bounded and the unbounded knapsack. The reason why I decided to put them together is because the approach used for them is quite similar. And I'm going to start with the bounded knapsack. So in the bounded knapsack, we have again the same items and their description. And the goal is actually the same. But in this case, we actually have another variable, let's say xi, which tells us how many items can we actually use from each item. And in order to solve this with the normal way of like splitting each item into x items and then doing knapsack on the sum of items, it's quite slow and it doesn't lead us to the correct result fast enough. So I'm going to introduce a trick which is named in the problems the log2 trick. And how does this work? So let's say we have an item with weight 14, value 7, and there are like 14 items we can take. Like the cap on the items is 14. And in this case, what we can do is actually to use the binary representation of 14. So 14 has binary representation of 1, 1, 1, 0. But the problem with the binary representation is that we can't actually create all the sums. Like we have 8 plus 4 plus 2. We can't create, let's say, a 7. And this is quite problematic. So we need to figure out something slightly different, which is writing 14 as the sum of power of 2's, such that we don't extend over 14 while we get all the possible numbers. So what I'm going to do is to start adding powers of 2 from the smallest one to the biggest one. So if we have 14, then we can start with 1 and we are left with 13. We can also add a 2 and we are left with 11. We can also add a 4 and we are left with 7. And we can also add a 7. And you can check out that we can actually create all the possible sums, which are equal to 14, while also not having too many items. Like on average, we are going to get around log2 items, like log2 xi. And instead of having n times xi times the weight, we are only going to have the n times log2 of xi times weight. And from that point, we can actually use the solution explained at the previous knapsack problem. Now, for the unbounded knapsack, the things are slightly different since we don't have a cap over the items. And we need to think differently because it only depends on the amount of weight we are allowed to use. And in many cases, since the weight is obviously not too big, you can actually use the log2 trick in order to reduce the amount of items. Or another option would be to just update the items on the run. Like if you have a position and an item, you just take each item and update all the values with something like to for loop. So you have a for loop over the items and a for loop over the weights. So that would lead again to n times w if you do it with 2 for loops. Now I'm going to explain the solution of a problem which involves the log2 trick, and I will also explain some problems which are either harder as an exercise for the more advanced readers or with different optimizations based on the constraints. So here we have a task from the Polish Olympiad in Informatics, or POI, as it's called in short. And the task is banknotes. So we have n types of banknotes, and we have for each item the amount of banknotes we are left with. And we have to find out the small, we have to find, let's say, what we have to find. Oh, we have to find the minimum number of banknotes sufficient to pay the sum K, which is given in the input. And if we are going to do an abstract over each banknote and each copy of the item, we would get a partial score. We are not going to get 0 points as in code forces, since in Olympiads you have to pass and different tests have different constraints. But we are not also going to get the full score, the 100 points. And we can assume that we can pay the sum, so we don't have to output something like -1. So here we can actually use the log2 trick. So let's say we have CI items, we can divide each CI using the log2 trick I explained earlier. And from that point, we have a classical knapsack implementation. But the difference is that for this problem, we need to actually be careful at what we are going to print in the second part, since we are not just asked to print the minimum number of items, but we are also required to print the reconstruction of the solution, which is harder. And now I'm going to go over my solution and explain how I did these things. So now I read the input, and I began with creating the log2 parts in order to allow me to do the knapsack. You need to observe that for the case of this problem, since we have to actually reconstruct the solution, the implementation parts are slightly harder to understand for the contestants who are not experienced with knapsack. And since we are in the Polish Olympiad of Informatics, where sometimes the memory limits are quite small, I had to use short in order to not go over the memory. But other than that, from that point, it's just classical knapsack implementation, as in I go over the items and then I go over the sums and then I check each possibility in order to reconstruct the solution. Because in this problem, reconstructing the solution is actually much harder than it usually is. So I don't recommend trying to solve this problem if you are not experienced with the concepts I explained earlier, because some parts in implementation are quite difficult. Now I'm going to move over some harder examples and also some problems to solve. For example, we have this problem from the Polish Olympiad in Informatics, which is a tree problem, but the solution is actually a knapsack. But before getting to the knapsack solution, you also have to observe some tree-related things. And in order to optimize the knapsack solution, in order to get the maximum score, you need to figure out how can you actually do the DP. But in short, you have a centroid decomposition over the tree, and then you have the knapsack algorithm with the log2 optimization in order to get yourself the maximum score. We also have this problem, which has been recently given at the Codeforces round 681 and has been also suggested by the guys from the Discord server along other nice knapsack problems. And we have n non-decreasing arrays, and we can actually choose a non-empty array and put that first element in the packet and remove it k times. And in this case, we can't actually use the normal knapsack because it would be too slow. But we can actually use a divide and conquer approach in order to solve this problem. Obviously with knapsack, but the divide and conquer approach helps the contestants figure out the solution in a fast enough time in order to pass. But again, this problem is also a div 1D, quite hard for most of the contestants, and I don't recommend this either for the beginners in knapsack. In order to conclude this video, I'm going to also talk about some more techniques you may actually use in order to get your knapsack skills up. And in order to actually solve knapsack problems which actually show up to the contest, to the newer contest, since most of the possible knapsack problem types have been already given in contest, because as Wikipedia says, the knapsack problem has been studied for more than a century, so it's something well known for everyone. You have to usually think at ways to optimize the problem, assuming you have different constraints in input. Like, there can be the case that you have some small weights, like it was in the knapsack tube problem in the outcoder, or small values, and you may actually have to reduce the number of items you're going to take. Like, I recently saw a problem where you had like 300,000 items, but the maximum weight was 3,000. And you couldn't do the normal knapsack because that would give us the time limit exceeded verdict. But after reducing the items to around n log g log g, actually, g log g items, where the g was the maximum weight, you could actually do the knapsack. So in short, in order to get your knowledge of knapsack on point, you can solve the problems I presented in this video while also searching for other problems like CSS or code forces, or in Olympiads. In Olympiads, it actually shows up quite often. Now, thank you for watching, and as always, I'm waiting for suggestions about other videos to do. And I would also like you to give me feedback on this video about how this tutorial was for you, because it is the first try for me to explain tutorial in a long time, and I might have missed some details. So please be kind and tell me what should I improve for the upcoming videos. Until the next time, stay safe, stay healthy, good luck, and goodbye.